All right, in this video here, we're going to be discussing the topic of how to multiply two vectors. This is something that so far in the course has been glossed over and kind of conscientiously walked around so that we can avoid having to learn any more math. But there is one simple way of multiplying vectors, which is going to be very useful in understanding the next topic, so I think it's worth doing. It turns out there are actually two ways that vectors can be multiplied. We're only going to go over one of them here. It is referred to, physicists usually call this the dot product. And the reason why is because when we write this type of multiplication down, we always use a dot. What I mean by that is we'll do it like vector A dot vector B. So just make note also the way, in scalar mathematics, all the different ways that you can write multiplying two things together have the same meaning. If you use a dot or an X or whatever, they actually have different meaning in the vector world. So you have to use this dot symbol when you're multiplying two vectors in this fashion. The other name for this is the scalar product. And the reason why that's a name for it is because when you multiply two vectors in this fashion, the result is actually not a vector. Notice that I'm not drawing a vector symbol over C. So this is a way of multiplying two vectors, and what you get out of it is actually a scalar, which remember means a non-vector, just a number. Okay, so that's what we're going to be talking about. Now, how do you do this process? So let's say you have vector A maybe is like this, and vector B maybe is like this. Okay, what is the dot product? Maybe I'll start out by giving you the formula for how to calculate it, and then it will be a little bit easier to understand once you actually see how you do it. So there's really two methods of calculating the dot product. As usual, it can be done either in magnitude and direction form, or it can be done in component form, depending on which one is more convenient. If you're doing it in magnitude and direction form, the way you do it is A dotted into B, which is often how people say it, equals the magnitude of vector A times the magnitude of vector B times cosine theta, where theta is the angle between vector A and vector B. And just take special note of what that theta means. One of the most common mistakes in using this formula is people will take some other angle that's given in the problem and assume that that's theta. Not necessarily. It has to be the angle that goes from vector A to vector B, or vice versa. The other thing to make note of there is you might have a situation where your two vectors are in quite different directions. Like maybe you have vector A like this, and vector B is way over here. That can also happen. In this case, you'll notice that angle theta can be as large as 180 degrees. So this is actually a rare case in the course where we have a cosine theta here, where theta is not necessarily less than 90 degrees. That's something to take account of. Okay, so that's how you do it in the magnitude and direction representation. The way that you can interpret wrapping your head around what that means is, I think the easiest way to see it is if you draw parentheses like this and think of it as being magnitude of A times magnitude of B cosine theta, because this, what I've written in the red parentheses here, this is actually a component of vector B. This is actually the component of vector B that's in the same direction as vector A. If you draw a right triangle like this, B cosine theta would be down here. So it's actually vector A times the component of vector B that's in the same direction as vector A. So sometimes I will also, a more compact way to write this formula, which will still remind you of what it is magnitude of A times, sometimes I'll write it as B parallel. And that parallel means the component of B that is parallel to vector A. So in this case, A is in the X direction. So we would be doing magnitude of A times the X component of B. And you can also, by the way, just as well do it the other way and make it the component of A that's parallel to B times B. Because of course it's arbitrary which one of these we called A and which one we called B. All right, so that's how you can wrap your head around the dot product in magnitude and direction form. It's basically telling you how much of one vector is in the same direction as another vector. The other way you can do this in component form, which might be a little bit harder to wrap your head around, but is often convenient, is you can write it as the X component of A times the X component of B plus the Y component of A times the Y component of B. And here you will notice that I think this might be the first formula in the whole course other than Pythagorean theorem where we have X components and Y components actually appearing in the same equation. So we're actually mixing together the X and Y components with each other to give you the dot product. Just make note that it's a little bit harder to maybe see in this formula what the properties of the dot product are, but it has all the same properties as if you wrote it the other way. So if you have the vector specified in components, that method's going to be nice and simple to do. Okay. I'd like to tell you also before the end of this video, what are the basic properties of the dot product? Let's clear the screen for that. What are the main properties of the dot product to remember conceptually? So first of all, it has the maximum value when A and B are in the same direction. So in the magnitude representation, that would you would have theta equals 0. So cosine theta equals 1. So in this case, the dot product is just all you do is take the magnitude of A times the magnitude of B. So in that case, it reduces to just multiplying the two magnitudes together. It is negative if A and B are sort of roughly in opposite directions. So that would be when you have that theta value greater than 90 degrees. So they're, one of them, say, is in the positive X half, and one of them is in the negative X half, or something like that. Let me just draw it to make that clear. So like the case I did, I showed you here where you have like A, B. These guys will have a negative dot product because they're kind of sort of in the opposite directions. Whereas, let's say you have, let's flip it around and change vector A for a change. Say you have A and B like this, where they're kind of close to being in the same direction. In this case, the dot product will be positive. So again, note that it's kind of a measure of whether A and B are pointed in the same direction conceptually. And then it is 0 if A and B are perpendicular to each other, because then you would have theta equals 90 degrees and cosine theta equals 0. So it can be positive, it can be negative, it can be 0. It depends on the magnitudes of the two vectors. It depends on the directions of the two vectors. So there's actually a lot of information contained there. Okay. Let me show you an example of how to use it in another video.